Nuclear, the word comes from the Latin nucleus, meaning core or center. It's the same term used for the seed inside a fruit and perfectly describes the nucleus in our cells and atoms. So, when we say nuclear energy, we're directly referring to the immense power harnessed from the core of an atom. We bury nuclear waste deep underground, marking it with today's danger signs. But fast forward 5,000 years. Languages change, symbols lose meaning, and all memory of that buried danger is gone. How do we stop future humans from unwittingly digging up something that could harm them? Here's the ingenious part. Scientists are creating forever warning signs. Think of landscapes filled with unnatural, menacing structures that scream, "Stay away," without using words or symbols. Just by looking, future explorers will feel a sense of dread, a primal warning not to dig deeper. Let's just hope they can pick up on this one. Today, we're well aware of the risks of radiation. But would you believe that back in the 1950s and 60s, atomic gardens were a thing? That's right. Gardeners were using radiation to try and create super plants. They hoped for bigger tomatoes, disease-resistant crops, and more, all thanks to the power of the atom. These gamma gardens had plants arranged in circles around a radiation source. The closer you got to the center, the more zapped the plants were. While it might sound wild to us now, it was all part of the atomic age optimism. And as for the results? Well, while most mutations weren't beneficial, a few did lead to improvements. It's a quirky chapter in our history, showing just how inventive, and sometimes a bit reckless, humans can be in the quest for progress. Now, let's talk about how a nuclear power plant works. At its core, it's like any other power plant, even coal ones. They all use heat to spin turbines and generate electricity. But here's where nuclear plants differ. They harness the power within atoms themselves. Inside the heart of a nuclear power plant, the reactor, we have uranium-235. This little atom holds incredible energy, and we release it through a process called fission. We bombard U-235 with neutrons, and it splits apart, releasing heat and more neutrons, triggering a chain reaction. Imagine it as a domino effect, but with atoms. But how do we keep this atomic domino effect under control? That's where control rods come in. They soak up excess neutrons, slowing or speeding up the reaction as needed. It's a delicate balance, ensuring we have just enough heat to make our steam without overdoing it. And speaking of heat, it gets really hot in there. So, we need a cooling system to prevent meltdowns. Water is circulated through the reactor, absorbing the heat. This hot water then boils into steam, turning the turbines, and voila, electricity. Most of us are familiar with the nuclear incidents at Fukushima in 2011 and Chernobyl in 1986, but there's a lesser-known event that had its own alarming moment. 3 Mile Island in 1979. So, what exactly went down at 3 Mile Island? Well, a cooling system failure in one of the reactors led to a partial meltdown. It wasn't an explosion or a fire, but it was a critical situation where things could have gone terribly wrong. The root of the problem? A small human error, much like missing an attachment in an urgent email. In this case, that attachment was crucial safety information that didn't get communicated. Energy production isn't just about what powers our homes. It's also about its human cost, or death print. Surprisingly, nuclear power, often considered dangerous, has the lowest death print of all energy sources. Here's a quick rundown. Coal leads with around 100,000 deaths per trillion kWh, mainly from mining accidents and pollution. Oil follows with about 36,000 deaths, mostly due to extraction accidents and health issues from pollution. Natural gas is responsible for roughly 4,000 deaths, with the main concerns being extraction accidents and emissions. Solar causes around 440 deaths, typically from installation-related accidents. Wind accounts for approximately 150 deaths, mostly from installation and maintenance. Nuclear? It's at the bottom, with 90 deaths per trillion kWh, primarily due to uranium mining and production incidents. Despite the fears surrounding nuclear energy, statistics show it's the safest in terms of lives lost. It's a stark reminder that there's more to consider about energy than just output. Beyond our artificial endeavours, nature has been a nuclear powerhouse for eons. Take the sun, for instance. It's a massive nuclear fusion reactor, merging hydrogen atoms into helium and radiating energy that sustains life on Earth. And it's not alone. Every star in the cosmos operates on nuclear fusion. But there's an even quirkier phenomenon: natural nuclear fission reactors. Found in places like Oklo, Gabon, these are spots where uranium deposits underwent self-sustained nuclear reactions billions of years ago, mimicking our current nuclear technology, but entirely natural. So, nuclear energy isn't just a human invention. It's a cosmic and terrestrial marvel, showcasing nature's own mastery of atomic power. Nuclear disasters like Chernobyl and Fukushima are more than tragedies. They're lessons in the sheer force of nuclear energy and its global impact. Chernobyl, 1986. The aftermath of this catastrophic event wasn't just environmental, it rippled through society and politics. The disaster exposed the Soviet government's inadequacies, shaking global confidence in nuclear safety and, some historians argue, accelerating the USSR's dissolution. The radioactive contamination spread over Europe, leaving long-lasting environmental and health scars. Fukushima, 2011. Triggered by an earthquake and tsunami, this disaster underscored the need for stringent safety measures against all potential risks. It led to worldwide reflection on nuclear protocols and a push for more robust safeguards. These events were watershed moments, driving stricter regulations, public debate, and a shift in energy policies. They stand as stark reminders of the respect and caution nuclear energy demands and the far-reaching consequences when things go awry. The echoes of these disasters still influence global nuclear strategy, emphasizing that harnessing such power comes with immense responsibility. As we gaze into nuclear energy's future, we're on the cusp of a game-changer: nuclear fusion. This isn't your regular nuclear power. Fusion is about joining atomic nuclei, emulating the very reactions at the heart of our sun. So, what's the buzz about fusion? It's clean, sustainable, and potentially limitless, with water and lithium as fuel, elements we have plenty of. Plus, it produces minimal waste and carries a lower risk of large-scale accidents. But it's a tough nut to crack. We're talking about replicating the sun's core conditions, with temperatures reaching over 100 million degrees Celsius. That's where groundbreaking projects like ITER in France and K-Star in South Korea come in. These experimental reactors are our real-world attempts at creating mini-suns on Earth, using a donut-shaped device called a tokamak to control the superheated plasma where fusion occurs. The goal? To get more energy out of the reaction than we put in, a milestone known as ignition. It's like lighting a self-sustaining cosmic bonfire. If we master it, fusion could answer our energy prayers, offering a safe, non-polluting, and virtually inexhaustible source of power. It's not just science fiction. It's a potential reality that could propel us into an era of energy abundance. Wrapping up our journey into the depths of nuclear facts, we turn to a current contentious issue: the Fukushima wastewater release. It's a story of science, safety, and societal concerns. So, let's break it down. The star of the show in this wastewater saga is tritium. This stubborn isotope sticks around post-treatment, but here's the deal: it's a low-energy beta emitter. It doesn't have the chops to penetrate human skin, and its radiation levels, they're set to meet, even fall below, WHO's strict safety standards for drinking water. But Fukushima isn't stepping onto uncharted shores. Nuclear sites globally have been quietly releasing tritium-laced water for years. Some European and American facilities have reported higher tritium concentrations than what Fukushima is proposing. So, the million-dollar question, is the release safe? Science gives a nod, but it's not without debate. Critics will point out you wouldn't want to drink this release water. But let's be real. If you're sipping seawater, radiation will be the least of your worries, thanks to good old dehydration. In the grand scheme, the Fukushima release is a calculated move in a complex global context. It's a reminder of the intricate balance between harnessing nuclear power and respecting nature's boundaries. As we sign off, remember, in the world of nuclear energy, knowledge is power. Stay informed, stay engaged, and keep questioning. Because every tick of information helps us understand the world a little better. Thanks for exploring with TenTick Facts. Until next time, keep those curiosity cogs turning.